Okay, let's talk about this idea of thermodynamics. Let me go back to the front, okay? And simply with this whole idea of thermodynamics. Whoop, let me get a pen. Okay? Thermodynamics. What does thermo mean? Thermo means heat. You know, in the fall we had kinematics. Well, this is the study of heat. Okay? And we're going to get specific with how certain objects or certain materials change through the increase of heat or the decrease of heat. Okay? Classic phase change diagram. Okay? There are these things called changes of state in a phase change diagram. You got solids over here, you got liquids over here, you've got gases over here. Each of these has specific properties. By the way, this is going to be, this is temperature here. Let me put that in red so you can see it. There's the temperature here. This is energy over here, okay? So energy increases this way, right? Temperature increases that way, okay? There's two distinct things going on here, and we need to look at these diagonal areas, okay? What's happening there, okay? Just follow it over to the y-axis, okay? Because there you're having temperature changes. And the other interesting thing here is simply what's going on these flat spots. Okay? And, you know, it's just kind of an interesting situation. So as you increase energy, what happens to that material? Okay? The diagonal regions, what happens? You increase thermal energy and you increase particle motion. Remember, this is still temperature over here. This is still energy over here. So these diagonal regions, right? What's happening? You're increasing thermal energy and your temperature is going up. Okay? You have the slope of the line. Again, that's going to be specific to that individual material. But as you increase energy during these diagonals, right? You're a solid here. Remember, that's a little arrow. This solid here is increasing temperature. The liquid here is increasing temperature. The gas here is increasing temperature. Okay? So on the diagonal regions, as you increase energy, you're increasing temperature. Now, what happens to these, I don't know what happened here. Where's my next one? I thought I did that. The flat regions, okay? With the flat regions, what happens? You know, now there's a lot going on. On these flat regions, you basically, when you're going from a solid to a liquid, right? If you start over here and you end over here, you're mostly solid on this side, mostly liquid on this side. Okay? When you come up this way, right, from here to here, you're increasing your temperature and you're increasing the amount of energy. I'm going to cross that out. I don't know that I like time because that's kind of you're increasing the amount of energy, but you're not changing the temperature. Okay? That entire sample, at this point, the entire sample has to you have to increase the amount of energy, and all of it goes from a liquid on this side to a gas over here. And then you get gas only, okay? Just the opposite is true as well. If you're going from a liquid to a solid, if you're just doing it with water, okay? If you're going from water to ice, you basically, if you're going down this way, right, you start to freeze as you go from a liquid to a solid, okay? That entire sample has to change over, from a liquid to a solid before it will start decreasing temperature again. Does that make sense? You have to get during this phase change, right? You have to get the entire sample to start that phase change, to get that over with. I'm sorry if that doesn't make sense. Okay? There's a couple of different ideas here that we'll mess with. There's something called latent heat. You know, what does latent heat mean? What does just the word latent mean? Okay? Well, latent heat is heat absorbed or released as the result of a phase change. Okay? There's no temperature change during a phase change. There's no change in the kinetic energy of the particles. The energy released comes from that potential energy stored in the bonds in between those particles, between those molecules. Okay? Does that make sense? Latent heat, okay? Where's that being measured from then? Well, latent heat is coming into play here and here. What are those called? Well, you've got the heat of fusion. What happens during fusion? Okay? The amount of energy required to melt 1 kilogram of a substance. And then you get a heat of vaporization. The amount of energy required to vaporize 1 kilogram. What are we doing? We're going to a gas here, right? What are we doing here? If we're melting something, we're going to a liquid. Okay, so there's a delta Q associated with that phase change, and there's a delta Q on this one. Okay? They're not, you can't assume that they're equal. Okay? So here's that big diagram. You go from a solid to a liquid to a gas. Okay? What's happening at all these points? You know, you need to be able to figure out what's going on this first part here as we go from A to B. What's going on from B to C? What's going on here? Okay? Well, from A to B, what are we doing? We're still a solid, but we are increasing our temperature. From B to C, we're changing over from a solid to a liquid, right? But we're not changing temperature. From C to D, again, we're increasing energy, we're increasing temperature. From D to E, we're increasing energy, but we're not increasing temperature. What are we doing? We're vaporizing. We're going to a gas state here. And E to F, we're increasing the temperature of the gas. Okay? The energy input is what's key here. First law of thermodynamics. Conservation, do you know what AKA means? Also known as conservation of matter. The amount of matter gene in the amount of matter or energy within a system remains the same. Okay? There are things out there called heat energy, or heat engines rather. They're basically devices which convert thermal energy to mechanical energy. Okay? There's also, you know, there's always some waste heat because you know that our transfer systems are not perfect. We always lose some in the process. What's that called, do you know? The second law of thermodynamics. Entropy is a measure of the unusable energy within a system. It's a gauge of the disorder. This is in chemistry. I hope you had this in chemistry. But entropy was one of the most important concepts around, okay? So what happens? As usable energy is used, it produces unusable energy, which increases energy. What does that mean? Every time energy is transferred from one form to another, you lose a little bit along the way. Okay? When that little bit is lost, it adds to this idea of disorder or chaos or whatever you want to talk about. You know, you put 100% in, you get 90% out. It's one of the arguments over, you know, eventually are we going to run out of everything? Okay? But as you use energy, as it's transferred from one form to another, you lose a little bit along the way. As you lose that, that adds to the entropy of the system. Okay? You know, the second law of thermodynamics, basically that the amount of energy in the universe is maintained or increased. What does that mean? Well, basically, that's what I said. As usable energy is irreversibly lost, that entropy increases. Disorder, randomness, chaos, however it is you want to talk about it. The key is every time energy is transferred, you lose a little bit along the way. We're trying to get better at capturing that, okay? Lost energy in various systems, but we always lose a little along the way. That entropy, it's a great idea. It's a wonderful concept. Okay? That entropy is increased. Whoop, I think that's all. That's a good idea. Remember, thermodynamics, phase change diagrams, right? Got to know what's going on during these phase changes. You need to know what? Where your solids are, where your liquids are, where your gases are, okay? You need to know the characteristics of these things. Do you remember those from chemistry? Characteristics has to do with molecular movement and things like that nature. Remember, this would be your temperature, this would be your energy, okay? You need to basically know the first law and the second law. And it's, you know, it's one thing to memorize it, it's another thing to understand what's going on. Okay? You know, theoretically, energy is neither created or destroyed. Okay? You know that energy is transferred. Now you know that when energy is transferred, you lose a little along the way. That little bit that you lose along the way increases the disorder. That's called entropy. Okay? I'll get this one posted. Let's see how we do.